This is Physics 1020 and 1090. The lecture is for Friday, April 10th. We're in chapter 29 on nuclear physics. In this first video, we're going to talk about different types of radioactive decay. Okay, first let me give you an overview of radioactive decay. These types of decay were discovered by our old friend Ernest Rutherford, who also did the scattering experiments to show the nuclear structure of the atom. Okay, alpha, beta, and gamma are the first three letters of the Greek alphabet. We'll start with alpha, this is the Greek letter alpha. Alpha means that the nucleus ejects a helium-4 particle corresponding to helium-4 out of the nucleus. Remember, helium-4, that'd be 2 protons and 2 neutrons for a total of 4 nucleons, gets ejected out as an alpha particle. Now, these alpha particles usually go for a very short range in matter and will then come to a stop and deposit all their energy over a short distance. If they are in the body, they can do a great deal of biological damage. It's a heavy particle, can really do a lot of biological damage, but they're very easy to shield from because of their short range. They won't go through clothes, they won't go through paper, they won't go through much of anything. For instance, if they get onto your body on the outer surface, they won't make it through very far through the skin before they'll stop moving. So, large amount of damage over a very small distance. The second example is a beta decay. Beta decay, there's the Greek letter beta, is when the nucleus ejects an electron. The electron typically moves off and has a intermediate range, so it goes farther than alpha particles, doesn't go tremendously far, and you can deposit then the energy into, say, tissue with a beta particle. And the final example, gamma, that's the Greek letter gamma, is if the nucleus releases a photon. The photon, known as a gamma ray, usually has a much longer range and could travel a long distance. It can do biological damage, but oftentimes it can do biological damage at quite a large distance from its source because it can travel a long distance before it interacts. So these are the three types of radioactive decay. In the lecture today, we're going to focus on alpha and beta decay. All right. Before we get going, I want you to stop the video and go get your periodic table. Stop now and get it. Just to remind you, I have a periodic table. Your periodic table should look something like this, so we can identify what the different elements are by their atomic number, because we're going to be talking over and over about these elements. And it's just very hard to understand without your periodic table at your side. Let's go with first alpha decay. Alpha decay. And we'll start with uranium-238. Uranium-238 is a very long-lived isotope of uranium, but it's not stable. It decays, and when it decays, it ejects an alpha particle. Alpha particle, 2 protons, 2 neutrons. Well, instead of writing helium, we often just write the alpha symbol for an alpha particle, but it's equivalent to helium-4. And what's left over when the nucleus spits out the alpha particle? Well, what it becomes is thorium-234. So uranium-238, uranium originally had 92 protons, because that uranium is element 92. It ejects 2 of them, so it goes down to element 90, which, if you look in your periodic table, is thorium, thorium. Originally it had 238 protons and neutrons. It ejects 4 of them in the alpha particle, so it's 234. Thorium-234 is the result. And this half-life for this process is 4.5 times 10 to the 9th years. That's essentially the same as the age of the Earth. Now, what's so amazing about this process is this process is almost a type of alchemy. If you remember, chemists often try to do a lot of chemical reactions, but you can't change one element to another by chemical reactions. But during the Middle Ages, there was a lot of attempt to change one element to another, change lead into gold, for instance. And that was called alchemy. And eventually it became in disrepute because it's impossible. But it's not really impossible because nuclear reactions can change uranium into thorium. So this was a great discovery when Rutherford and his collaborators realized that you're actually changing the element from one to another. Well, uranium changes into thorium-234. Thorium-234 is itself radioactive and starts a whole chain of radioactivity. And we'll see a little more about that radioactive chain here in a few minutes. But eventually that change comes down and you have some radium-226. So it ultimately came from uranium. Radium-226. Radium, element number 88, was one of the elements discovered by Marie Curie and her husband. It was actually discovered in 1898, but it was isolated in 1902. What they did is they took some rocks that contained uranium and they chemically isolated down and purified those rocks until they were able to find just a tiny little speck out of a huge mass of rocks. You started with like a ton of rocks and you ended up getting like a gram or a milligram of radium-226 and isolate the radium. Radium's not stable. Radium-226 decays by alpha decay to what? You figure it out. Stop the video, figure it out, then come back. Well, radium-226 decays by alpha decay to element number 86, which is radon-222. 86 plus 2 is 88. 222 plus 4 is 226. That's how it works. Now, what couple of things to note. First of all, when this happens, radium-226 decays and you get this alpha particle ejected. It gets ejected with a fairly high energy of about 5 MeV. And that's the alpha particles that Rutherford used for his scattering experiments. He got a sample of radium from Marie Curie and that just sat there and shot out these alpha particles, which he could then use for his experiments. Has a half-life of 1600 years, so it's basically on the lifetime of a person, a fairly stable, constant source of radioactivity. What gets produced is this radon. Radon, if you look in the periodic table, is over in the column that has the noble gases. So radon could get produced in, say, in rocks. The radium in rocks from that ultimately came from uranium can turn into radon. The radon can then diffuse out of the rocks and to get into the air that we breathe. And this is radon gas. Radon gas can be a little bit dangerous because you breathe it in and then it gets into your lungs and get into the blood supply. Even though alpha particles don't travel far, alpha particles, the radon gas, will emit an alpha particle when it decays and can do biological damage. So there's a lot of concern about radon gas, especially building up in people's basements. So nowadays, oftentimes when you sell or buy a house, it'll need to be tested for radon gas in the basement. But radon is not stable. Radon-222 decays by alpha decay to what? Stop the video, then come back. Radon-222 goes to an alpha particle plus element 84, which is polonium-218. And that decay happens fairly quickly in 3 minutes. So that radon doesn't exist very long, but it can seep out of the rocks, get into the atmosphere in less than that 3 minutes. So it can be a danger. Polonium was another element that the Curies discovered. So their biggest discoveries were really radium and polonium. In fact, Marie Curie was from Poland, so that's how polonium got the name, because named it after her home country of Poland. I'd like to now, for our last example, consider a different isotope of polonium. It actually occurs in the same decay chain, but farther on down. Polonium-210. Polonium-210 is not stable, and it decays by alpha decay. What does it decay to? Stop the video, then come back. Polonium-210, element 84, decays by alpha decay to element 82, which is Pb or lead, lead-206. This has a half-life of 138 days, but once it reaches lead-206, lead this is a stable isotope of lead. So here the decay chain ends. So all those elements that got produced from the uranium-238 end with lead-206. Now, interesting thing about polonium-210 is it's actually a very deadly poison. Why? Because it's highly radioactive. So you can put it, what happened was there was a Russian, Alexander Litvinenko, about 10 years ago, who the Russian, some agents came over. He was living in, I believe, England, and they met with him, and they were having some tea and discussing, and they put a small amount of polonium-210 into his tea, and he drank it. And then it got into his body, into his blood supply, spread throughout his body, and over the days to come, he was irradiated by a huge amount of alpha particle, a very dangerous type of irradiation, and he eventually died. It's a very, its half-life makes it a nice poison, if you can say nice, because 138 days, that means it's not going to decay so fast that it's hard to get it to him. If it was 138 minutes, why, it'd be hard to produce the poison and get it to the person and have them drink it before it decayed away. But 138 days, if it was 138 years, well, you have plenty of time to take it and move it around, but 138 years would mean it wouldn't really give off that much radiation. It would be decaying so slowly that the decay rate would be slow. 138 days, polonium-210 is actually a very deadly poison. That is a little bit about alpha decay. Wanted to give you a story of how Rutherford proved that alpha decay was actually a helium nucleus being ejected by the atom. And for his work understanding radioactive decay, he got the 1908 Nobel Prize. He got it in chemistry, which always annoyed him. But let me go to the making of the atomic bomb. And I wanted to read to you a little bit about his big announcement of a new discovery at the Nobel Prize ceremonies. An eyewitness to the ceremony said Rutherford looked ridiculously young. He was 37 and made the speech of the evening. He announced his recent confirmation, only briefly reported the month before that the alpha particle was in fact helium. The confirming experiment was typically elegant. Rutherford had a glass blower make him a tube with extremely thin walls. He evacuated the tube and filled it with radon gas, a fertile source of alpha particles. The tube was gas-tight, but its thin walls allowed alpha particles to escape. Rutherford surrounded the radon tube with another glass tube, pumped out the air between the two tubes, and sealed off the space. After some days, he told his Stockholm audience triumphantly, a bright spectrum of helium was observed in the outer vessel. Rutherford's experiments still stun with their simplicity. In this, Rutherford was an artist, says a former student. All his experiments had style. So that is an example of the scientific method at work. Let's move on now to beta decay. Beta decay. The classic example of beta decay isn't really a nucleus at all. It's a free neutron. You can have a free neutron, which would have 0 protons and 1 nucleon. 0 plus 1 is 1. Decays into a proton. A proton you can think of as a hydrogen nucleus, but it's just a proton. Now, if a neutron goes to a proton, that produces plus charge. You can't just invent charge. So an electron also is produced, and that's what's ejected typically by the nucleus, the electron. Electron's negatively charged to balance the charge. Electron is neither a proton nor a neutron, so it has a 0 up in the total number of nucleons. We usually put a -1 as a subscript. Not that it has any great meaning, but it makes the bookkeeping work because you have a 0 for the number of protons on this side. If you produce a proton and you have a -1 for the electron, that means the bookkeeping will be 0 on both sides. Don't try to think anything more too deeply about that -1. It's just a bookkeeping. Also, what gets produced by this beta decay is something called an antineutrino, which again has 0 charge and almost 0 mass. And we're not going to talk much more about the antineutrino, but it's a third particle. And this is known as beta minus decay because it's an electron with a minus charge. Free neutron has a decay of about a half-life of about 10 minutes. So let's do another example. Remember when we talked about uranium-238, and it decayed by alpha decay to thorium-234. The thorium-234 is not stable, and it decays, but it doesn't decay by alpha decay. It decays by beta decay. So what would your thorium-234 decay to when it went by beta decay? Stop the video, work it out, and then come back. Thorium-234, which is element 90, decays to element 91, 234, protactinium. So, since a neutron is turning into a proton, you go up in atomic number from 90 to 91. The mass number does not change at all, and so you've gone up to the same mass number, but one higher in the atomic number, and you shoot out the electron out of the nucleus. This half-life is 24 days, which is much shorter than the 4.5 billion years for uranium. So you see that every time a thorium-234 gets produced, it almost immediately decays to a protactinium-234, and so on goes the decay chain. Let's look at another example of beta decay. We talked about carbon-14 when we talked about carbon-14 dating. Carbon-14 decays by beta decay, beta minus decay. Let me point out one thing while we're here. Usually nuclei that are neutron rich, too many neutrons to be stable, tend to decay by beta decay. So carbon-12 is the common stable isotope of carbon. Carbon-14 is neutron rich, so it then decays by beta decay. What does it decay to? Stop the video, work it out, and we'll come back. Carbon-14 decays by beta decay to nitrogen-14. Again, 14 is the same in both. 6 protons, you go up to 7. 7 minus 1 is 6, works out. So you go up to nitrogen-14. Remember when we talked about how the carbon-14 was produced? It was actually produced by a cosmic ray hitting nitrogen-14. So nitrogen-14 cycles through carbon-14, then decays back to nitrogen-14. Here's another isotope. CS is cesium. This is cesium-137. It's element 55. It decays by beta decay to what? Stop the video, work it out. Cesium-137 decays by beta decay to element 56, which is barium-137. This decay has a half-life of 30 years and is actually very important when considering the Chernobyl disaster. We're going to have a lot to say about the Chernobyl nuclear disaster, which was one of the most deadly nuclear reactor disasters that ever happened. But I want you to see that cesium-137 has a fairly long half-life of 30 years. Now, there's a lot of different radioactive isotopes released in the Chernobyl disaster, and most of them had shorter half-lives, and those shorter half-lives produced a whole lot of radiation right at first, but after the weeks and months went by, they decayed away. But the 30-year long half-life of cesium-137 means that it remains radioactive for decades after the disaster. Now notice, if you had a very long half-life of 30,000 years, say, then it would last a long time, but it wouldn't be producing that much radioactivity, because if you have a very long half-life, very few of the elements of the isotopes actually decay, and it doesn't produce much radioactivity. So this 30 years is a particularly dangerous isotope, long enough to cause a toxic decay and toxic waste for decades, but not so long that you still get quite a bit of radiation. Let's do one more example. Iodine-131, which we discussed before, used to treat thyroid cancer. It decays by beta decay to what? Stop the video, work it out. It decays to element 54 131, xenon 131. So again, 54 minus 1, there's supposed to be a 1 there, is 53. 131 plus 0 is 131. It works. Half-life of 8 days, and we talked before how this half-life is used to treat thyroid tumors. Now we know something a little more specific. What's actually doing the damage to the thyroid tumor is the electron that gets reduced, then goes and does the biological damage. It has an intermediate range, so if it was alpha particle decay, it would be restricted solely to the thyroid, and but in this case, it moves maybe a few millimeters or so around outside the thyroid also. So that's an example of beta decay. Let me go back to this idea of decay chains because it's kind of interesting. There are basically 3 very long-lived isotopes in our rocks on Earth. There's uranium-238, which we talked about before, element 92, 238. Has a half-life of 4.5 billion years, which is about the same half-life of the age of the Earth. And it decays ultimately through a long decay chain down to lead-206. So rocks that contain uranium-238 also contain all those other elements in the decay chain down to lead, and then no shorter because lead's stable. There's also another isotope of uranium, uranium-235, which has a shorter half-life, about 0.7 billion years. It decays down to 207 lead-207, and then ends the decay chain. But there's also a whole other chain of alpha and beta decays going on until it gets to lead-207. Notice that in 238, the mass number can only change by 4. It changes by 4 during alpha decay, and it doesn't change at all during beta decay. So you can go to 238, it can go down to 234, to 230, to 226, to 222, and down all the way, if you figure it out, to 206. 235 is different from 238 by 3, not 4. So it's got a whole different set of isotopes in it compared to 238, and it ends at a different isotope of lead, also stable isotope, but a different isotope. And then there's thorium. Thorium is element 90, and thorium-232 has its own decay chain. Half-life of thorium-232 is 1.4 times 10 to the 10th, or in other words, 14 billion years. It ends in 208 lead. So all 3 of these exist in our rocks and can create these chains of decay chains of radioactive materials. There's a 4th possibility because there's 4 types of decay chains you can have depending on whether it's a multiple of 4 or 4 plus 1, 4 plus 2. Neptunium-237 is an example of the 4th type. Its own half-life is much shorter, 2.1 times 10 to the 6, so it doesn't really appear much in our rocks. It is all decayed away, basically. But it would decay down to lead-209, yet another stable isotope of lead. So this is the decay chains that occur on the Earth and produce a lot of the radioactive elements that exist on Earth. So that's a little bit about alpha and beta decay. In the next lecture, we're going to talk about gamma decay plus some more exotic types of radioactive decay.